Hi everyone! IBM partners want to understand how to grow their businesses and how to reach new markets. One way to do this is to build reusable enterprise applications for multiple clients. To deploy and operate applications on multiple clouds or on premises, Kubernetes operators can be used. In this session, we will introduce the operator pattern. We will explain how to get started with operators and how we can help you to build operators to unleash the power of the applications that you have already built. We are a team of highly skilled IT professionals and we can help developing operators. Let us introduce quickly. And here's the team. So team, let's give everyone a wave.
Yeah!
Yeah.
Woo!
Yay!
Hey.
Woo!
Boom!
Yeah, and I'm Thomas. I am also in that nice team I like to develop.
Hi, I'm Divakar from India, cloud engineer at IBM. Parts of the Build Labs team working together on OpenShift and Kubernetes operators.
Hi everyone, I'm Adam Deleu. I'm a Build Labs engineer from the UK.
Hi, Alan from Build Trends team in France. I love working on operators on Kubernetes and OpenShift for our business partners.
And I'm Niklas. I love learning and I love the power of Kubernetes operators.
Hi, I'm Angela Bates. I'm from Build Labs based in London, and I've got the privilege of leading this wonderful team.
Hi, this is Sandeep. I'm a cloud engineer at IBM, and I'm the part of Kubernetes operator development team.
Okay, so here's the agenda. First, we will set some context and describe the benefits of operators. Next, we will give some demos of sample operators that we have built. In the third part, we will cover marketplaces and explain the high-level architecture. In the last part, we will outline how we can work together. To explain a key benefit of operators, let me use an analogy. How do you reach as many users as possible for mobile apps? The answer is simple. You publish your mobile apps in marketplaces like the Apple App Store and Google Play Store. What is the counterpart for enterprise applications? How can you reach masses of enterprise application clients? Well, again, via marketplaces. Operators support the packaging of Kubernetes-based enterprise applications so that they can be shared and promoted in various marketplaces, catalogs, and hubs. With operators, offerings of partners can be made reusable, offered digitally in a self-service fashion. Kubernetes is the standard way to run enterprise applications. To reach as many users as possible, your applications need to be able to run on Kubernetes. OpenShift is the Kubernetes enterprise distribution. While Kubernetes can be compared with a powerful engine, OpenShift is a complete car which comes with everything needed for enterprise production workloads.
How to build reusable enterprise applications. That leads to the question, what is enterprise? And the question, what is reusable? Simplified, we can say enterprise means complex. Usually enterprise applications are not easy to develop and to operate. The operation of enterprise application contains mostly different kinds of error-prone human operator tasks. During an installation, when maintaining or managing the application or getting insights of an application. Because an enterprise application mostly consists of stateful and stateless applications, different network configuration, backups, scalings, dependencies and many more. So how to avoid errors of human operators and provide an easy of use and reusable way for automated complex tasks so that we can simplify day 1 and day 2 experience for enterprise application usage with automation for installation, configuration, updates, backups or other automated tasks. The answer is the automation for day 1 and day 2 operations should be a part for an enterprise application development right from the start. That means you should start with building operators to automate all the complex tasks from the start, and an operator shouldn't be seen as an extra development. An operator should be a common part of an easy-use enterprise application you are going to build. By the way, that boosts the exchange between development and operation. That supports the DevOps culture in your team. With automation made by operators for your enterprise application gets a bit closer to be a software as a service right from the start, because all of that automation and the ease of usage. The operators are a part of building an easy, reusable enterprise application.
So why cannot we just use Helm in order to deploy an application? Helm is a great set of toolings which lets us set up and install and configure the first time an application on a Kubernetes-based platform such as OpenShift or any other flavors of Kubernetes that we can find on the market. But that's not sufficient when we want to talk about future maintenance, any kind of maintenance, enhancement, improvements, new features, whatever we can think of, that we might want to add to the application. And that's precisely the cloud native philosophy. When we are talking cloud native, it means that we should be agile and be able to improve our applications even on daily basis. And that wouldn't be possible if we rely on technologies such as Helm. Again, Helm is great, but it's not sufficient. When we talk about day two operations, we need to use adequate toolings, and that set of toolings come with the operator technology, which enables us to build applications which are ready to have any kind of enhancement and improvement that we might add in the future, so they could be easily deployed, updated, and gives also more capacities in order to be able to do some even maintenance on these applications, such as, for instance, making backups or whatever you can think of. So that's why we are not just focusing on day one, but we are going one step beyond, and we are talking about day two operations.
Now we need to understand what values operator will add on into our existing Kubernetes environment. In one word, they extend the capabilities of a Kubernetes cluster to a whole new level. They are software extensions which help us to encode business logic of our application through custom resource definitions. It increases the functionality of a Kubernetes platform without modifying the code of Kubernetes itself. Basically, operators enables us to create, configure and manage our applications in a Kubernetes environment as per specific domain need. So the automation in the Kubernetes operators can basically help us like deploying and scaling applications as on demand, backup and restore of the applications particular desired state, handling applications upgrades along with its relative changes such as database schema or some other configurations as well, and publishing a service to application that even doesn't support Kubernetes API to perform the app discovery task as well, simulating any kind of failure scenarios throughout the cluster to test the resilience. Operators also help us to eliminate manual intervention which required at operations part, means no need to have personnel for backup and restore and upgrade of some other day 2 operations. So more automation means lower operation cost, easy adoption of the Kubernetes and faster the innovations.
Organizations migrating to Kubernetes have seen increased agility, improved development, and reduced friction in the process. But running its day-to-day operations is not as easy as it seems. Kubernetes application lifecycle consists of many stages like design, deployment, and operations, which developers have to consider when deploying clusters and maintaining them in the long term. Indeed, it is typically the production operation stage where developers face challenges when the underlying architecture induces different complexities as it grows. The complexities represents an opportunity for vendors to help organizations properly maintain Kubernetes clusters based on the workload, and even take control of monitoring and management to reduce redundant steps. All of these operations performed by organizations or vendors to simplify and refine the Kubernetes stack for automating the platform's management come into day 2 operations. Typical day 2 operations are focused around maintaining, monitoring, and optimizing the system. Day 2 operations continue throughout the product lifecycle, as the system behavior must be continuously analyzed and patched. Kubernetes operators provide all the necessary tooling to automate complex day 2 operations. Operators are deployed into Kubernetes clusters and implement day 2 activities like updates, backups, and failovers. Operators are managed through an operator framework toolkit developed by Red Hat. The toolkit consists of an SDK for building custom operators to meet specific day 2 needs, such as native monitoring and logging, auto backups, auto scalability, fault predictions, self-healing, auto upgrades, smart reporting, and whatnot. Sky is the limit.
OpenShift is the enterprise distribution of Kubernetes that allows you to run application on multiple clouds or on premises. It comes with a built-in operator hub, allowing users to find and install operators with just a few clicks. In Operator Hub, you can find operators from various sources, for example, validated solutions from the Red Hat Marketplace, as well as community-provided operators from operatorhub.io. There are 3 main benefits that operators provide. First, the automation of day 2 operation tasks is a huge benefit. Operators are a powerful technology to automate the expensive and error-prone human operations. Features like autopilot, self-healing, and the automatic management of stateful applications are good examples. Operators support the packaging of Kubernetes-based enterprise applications so that they can be shared and promoted in various marketplaces, catalogs, and hubs. With operators, applications of partners can be made reusable and offered digitally in a self-service fashion. Kubernetes has become so successful because it's a general purpose platform and because it has been designed from the ground up with extensibility in mind. The operator pattern is used internally in Kubernetes, and it can also be used externally for your custom applications. This pattern is Kubernetes native, which allows leveraging the huge Kubernetes community as well as available and existing tools.
Here at IBM Build Labs, we've created some example operators which you can find in our GitHub repo, which we'll show you in a few minutes. In the meantime, I'm going to use those operators to give you a demonstration of some of the typical capabilities that operators provide. I'm also going to show you how to package, distribute and version an operator so that it appears in the OpenShift console of your customers, which hopefully makes it easy for the administrators to potentially discover your solution and also to install and manage that solution going forwards. So the main capabilities of our example operators fall into 2 categories, either day 1 or day 2 capabilities. So day 1 capabilities are all about that initial task of installing the resources required for the solution. So in our case, our operator installs a simple web application server on the front end and also a database cluster on the back end. Day 2 is all about automating some of the tasks which might be required to keep the solution up and running. So in our case, our operator automates the task of performing a database backup and also scaling up some of the components. The operator really provides a useful abstraction for the administrator of the OpenShift system. So when you're working with operators, you only need to create very simple resources that actually trigger the operator to create lots and lots of Kubernetes resources behind the scenes. So if your solution consists of lots of different Kubernetes components, or is stateful, or requires various day 2 activities to keep it up and running, then using an operator could really be the difference between success or failure for your customers. Here in OpenShift you'll find the Operator Hub. It's essentially a catalog of operators that the administrator of this OpenShift cluster could install. These operators come from the likes of Red Hat, from IBM, and also from independent software vendors as well. And the operators are categorized by their source. So for example, you'll see that many operators come directly from Red Hat, so these are Red Hat software offerings, but there's also a list of certified operators. So these come from independent software vendors who have gone through a process with Red Hat to certify that their operator and their software offering meets certain criteria imposed by Red Hat. There's also a community source of operators as well. So this is an external GitHub repository into which you could put an operator, meaning that it would then become visible via the OpenShift operator hub. So that's quite an easy way of publishing an operator. And then finally, there's the marketplace. So this is like an app store basically. So if you publish the operator into the Red Hat marketplace, then Red Hat take care of the commercial aspect as well. So you can charge people to use your software, which is installed by this operator. Finally, if you don't want to include your operator in any of the sources that I just mentioned, and you'd rather deliver your operator directly to a particular customer of yours, then you can have that customer create private catalogs as well. So that's what I've done for our sample operators. You can see that we have a couple of operators that are only visible within this cluster. Now, whichever approach you decide to take, you have to package up your operator in accordance with a component from Kubernetes, which is called Operator Lifecycle Manager. In a moment, I'm going to install the two sample operators that I just showed you in the Operator Hub, but before I do that, I want to explain briefly how we went about packaging those operators so that they are compatible with the Operator Lifecycle Manager component. So all you need to do is to create a bundle of files, and there are tools to help you create that bundle. In that bundle of files, it essentially describes the operator. So for example, does the operator depend on any other operators to do its work? Also, every operator will define what are called custom resource definitions. So these CRDs are essentially extensions to the standard Kubernetes resources that you might be familiar with, for example, pods or stateful sets. Once you have this bundle of files, then you use again some tools to create a container image containing essentially just those files and put that bundle image into a container registry. Then from that bundle image, you then build a subsequent image, which is called an index image, or sometimes known as a catalog image. And what that does is it builds an API around the data or the content of those files. And that API is compatible with Operator Lifecycle Manager. So once you have that catalog image, what you do with it next really depends on whether you want to put your operator into one of those existing catalogs, like the Red Hat Marketplace or the certified solutions, in which case you would work directly with Red Hat, or if you're okay with creating a private catalog, as we've done with our samples, then you can take that catalog image and plug it into the Operator Hub on OpenShift. In OpenShift, under the cluster settings, you can actually see the different sources of catalogs which are feeding into the Operator Hub. So here you can see the last two entries here are the custom catalogs which contain our sample operators. And you can see they take their content from one of those catalog images that I was just telling you about, which happen to be located in my container registry. So let's go ahead and install the first of our sample operators, the database operator. As you can see, each operator provides a description of what it does, what it installs, what its capabilities are. When you hit the install button, there's only a couple of questions. Do you want to install this operator in just the current namespace, or do you want to make it available across all namespaces? And what is your policy about installing updates to the operator? Because the provider of this operator could publish updates to their registry. Do you want your cluster to install those updates automatically, or would you prefer to approve them? So let's go ahead and install this operator, which takes just a few moments. Now, just to be clear, this process is installing only the operator. The operator is essentially a pod which contains a controller. It's some logic that we've written in a language called Golang. It's not actually installing a database at all at the moment. It's only installing the operator which will sit there and wait until the administrator of the cluster creates a resource on the cluster which that operator is waiting to react to. So now that the operator has been installed, we can see it in this list here. And here we can see the different resources, the custom resources that this operator has defined and is sitting and waiting to respond to. Just to explain what these resources mean, the database cluster resource is a definition of essentially deploying an instance of the database in a clustered fashion. So there will be multiple instances of our database. One of them will be the leader, others will be followers, and obviously there are multiple instances for high availability. Database is the definition of a kind of a schema, so that installs some data onto the database. And database backup is another resource that the administrator can create in order to create a backup strategy. So let's go ahead and create one of those custom resources. You can see in this YAML file that the kind of the resource that we're going to create is called database cluster. So that's not a resource that you'll find by default on the Kubernetes cluster. It's a custom resource that was defined by our database operator. And like every resource that you create on Kubernetes, it has some fields or some properties that you can fill in. But the whole point is that this custom resource abstracts a lot of the complexity away from the administrator. So you can see that our resource only has two fields. The first is the image for the container which is going to implement our database. In our case, in our example, we have written our own database server. It's extremely simple, and this is where the database service exists in a registry. And also we can specify how many instances of that database that we want to have for high availability. So let's go ahead and create this resource directly on the cluster. And what should happen is Kubernetes will inform our operator that one of the resources that it monitors has been created, and it's up to the operator now to create the Kubernetes resources that are required to implement a database cluster according to our properties or our criteria. So over on OpenShift, you can see in the custom resource definitions that our database has previously defined the three extensions or custom resource definitions that we talked about. And you can see that under database cluster, there is now an instance of one of these custom resource definitions, which is the one that we just created. Hopefully by now, the operator will have created all of the resources to implement a database cluster. So the database itself is actually deployed as a stateful set that you always find in this namespace. And you can see that it's implemented as a number of pods, and those pods are being created right now. So there's a couple of things you need to know about this sample database. It provides an API, which we're going to be calling from the front-end web application. And also, when we create this database cluster, it initializes itself with some sample data. So first of all, I want to check that the sample data is present. So we can choose any one of these pods, which implement our database cluster, and go to the terminal for that pod, and then we can call the API to retrieve the data. In this case, it gives back a very simple JSON data structure containing a list of names. So let's move on to look at one of the day 2 capabilities of our database operator. What if you wanted to back up the data that we just saw in the database? You could create a script or have a human periodically execute the steps to back up the data, but potentially that could be error prone. So instead, we can use the operator to automate this task. What we've done is create another custom resource, which is called database backup, and the administrator can use this resource to specify their database backup strategy. What the operator is going to do is it's going to create a cron job on the cluster, which springs into life on a schedule that has been defined by the administrator to back up the data from the database into a backup repository, for example, Cloud Object Storage. So let's take a look at how you would go about doing that. So let's take a look at how you define that backup strategy. So we do that using the custom resource database backup, and it has three main sections. The first is a list of repositories to which you want the database to be backed up to. So in our case, we're defining just one repository, which happens to be Cloud Object Storage on IBM Cloud. And then you can specify either an immediate manual backup or a scheduled backup, which should happen according to the schedule defined here. So in this particular case, obviously, we're requesting both the manual backup immediately and a scheduled backup as well. So let's go ahead and create this resource on the cluster, and we'll see what happens. In response to us creating that database backup custom resource, the operator has created some Kubernetes resources to implement our database backups. So it's created a cron job and a job. The cron job is because we requested a backup that happens on a schedule. So this cron job will launch at the top of every hour, and if you look at its definition, it will use a container image from a registry. That container image executes some code which connects to the database and then uploads the data into Cloud Object Storage. The job is exactly the same, except that it happens immediately because we requested an immediate manual backup. So that gives us an opportunity to look at the logs for that pod and see if it was successful. So here you can see the data has been retrieved from the database. It's the same list of names we saw before. A bucket has been created on Cloud Object Storage and the database backup was successful. In fact, if we go over to IBM Cloud, we can look at the Cloud Object Storage and see that a bucket has been created, and we can actually look at the object inside of that bucket, download it, and verify that the data has indeed been backed up. Let's take a look at one of the other day 2 capabilities of our sample operators, this time auto scaling. Again, the operator uses a cron job to launch a pod on a schedule, and this pod makes scaling decisions. By using our own pod, we can have complete flexibility about what influences a scaling decision. Perhaps it's metrics that come from the front-end application, or maybe from the back-end database, or maybe it's a combination of both. Let's take a look at how it works. The auto-scaling example works to scale up and scale down the front-end web application. So we need to install that now, and of course we have an operator to do that. It's called the application operator, and it defines another custom resource which the operator will react to and deploy a web application server. So let's do that. So here's the custom resource that the application operator responds to. Again, it's pretty straightforward. You can specify the number of pods that you want. You can specify the image which implements the web application server, and you can specify some additional properties like the title and the database name to connect to. So let's go ahead and create that now. As before, back on the OpenShift cluster, we'll see that there is a custom resource definition called application, and we have created an instance of that application. The operator responds to the custom resource by creating a deployment in the application namespace, and the deployment contains just a single pod which implements a web application server. We also have a route which exposes that web application server, and it has a single endpoint called /hello. And if we trigger that endpoint, then you can see that the web application gives us the greeting and also echoes back some of the names that come back from the database. We've set up the web application server to expose a metric which represents how many times that /hello endpoint has been invoked. And that metric can be collected by the Prometheus monitoring software, which is very popular across Kubernetes and is installed by default on OpenShift. So first of all, let's inspect the value of that metric in the Prometheus dashboard. As you can see, at the moment, the /hello endpoint has been triggered 12 times. Let's take a look at the cron job that was created by the application operator. As I mentioned, this cron job is going to execute on a schedule to make the scaling decision. So if we look at its definition, as you'd expect, it specifies a container image to launch to make that decision. The code within that container image is going to connect to the Prometheus monitoring system and query the metric that we just saw for the /hello endpoint. We can either wait for the scaling cron job to execute at the top of the hour, or we can use a command to make it execute immediately, meaning we can check out the results. So if we look at the cron job for the application scaler, we can see now that it has launched a job, the one that we just requested, called manually triggered, and that job launches a pod, and that pod is our custom code which makes the scaling decision. Now, as I said, that gives us complete flexibility to write some code which considers any number of metrics to determine the scaling decision. So let's have a look at the logs for that scaling pod. So as you can see, we have connected that pod to Prometheus, and it has accessed the metric which represents how many times that /hello endpoint was invoked. And you can see that again it says 12 times. So the logic inside of this pod is actually really simple, and it decides that if that endpoint has been invoked more than 6 times, then the application needs to be scaled up. So how does the application scaler actually perform the scale up? Well, if you remember, we already created a custom resource called application, which the application operator responded to by creating a deployment of exactly 1 pods. Now, if the application scaler pod decides that a scale-up is necessary, it actually locates this custom resource instance on the cluster and edits its definition to specify that actually 3 pods are now required. And you guessed it, it's actually the application operator that gets notified of this change and changes the size of the deployment accordingly. So now you can see that there are 3 pods responding to Web Application Server requests.
It is always good to have standardization. In that slide we see the standardization definitions of capability levels, which to help us to get a common understanding of what we are going to deliver and what others are going to consume by using our operators. The operator SDK framework does define these standardizations. In that slide we can see 5 operator capability levels. A capability level does reflect what we need to provide as functionality for our users. For example, to achieve capability level 2, we need to implement streamless upgrade with patches, minor versions, updates for our operator. So what is the operator SDK? The operator SDK has the objective to be a toolkit for easy development of operators. It uses, for example, customize for configuration of needed YAML, makefile for automations, and operator package manager for packaging the operator. The operator SDK framework supports different development languages. In that slide we see 3 commonly used programming languages and which capability level of implementation they do support. The widest used one is the Go language. That is the language and the SDK we have seen in our demo made by Adam. When we build an operator, we need to know what we are going to operate in Kubernetes for our application, and we need to know how to realize such automation with the right development language. So which SDK we are going to use. Also, we need to know, can we achieve the capability level we want to provide with our operator with the chosen SDK? The operator SDK is used in combination with the operator lifecycle manager for easy production usage. We remember the operator SDK contains standardized definition of capability levels. The operator SDK is a part of the operator framework that can be used to build operators. And the operator framework works in combination with the operator lifecycle manager, and the operator lifecycle manager has the focus to provide an easy production usage of many operators in different versions available on different catalogs. Let's have a closer look at the simplified technical metamodel of an operator. An operator will manage our desired operational work for our application or system. Surely we need to know what the desired state of our application will be in the container platform. The picture shows 5 major elements of an operator. The first box represents our operator application, because finally our operator is an application which we use to manage our application we want to deploy in the orchestration platform. So we need to provide a custom API that extends the Kubernetes API, because we want to customize the needed import for our application we want to deploy to Kubernetes or manage. The manager and controller to implement the logic how to realize the desired state in the container orchestration platform. So that is what we need to implement inside the operator. The webhook helps us to initiate some automation that can be initializations, validations, or API conversions of our operator, which does implement the application automation management. So that are the 5 major boxes you can see.
The Build Labs team provides a reference architecture which is available on the public GitHub, where we showcase what we did around a very simple application, but how you can take this simple application and maybe try it on your own to deploy an application of your own on a cluster-based environment on top of a cloud. So if you want to discover this application, please go to github.com/ibm/operator-sample-go, as you see at the bottom left of the screen, and try it out by yourselves. So where do we find operators when we want to install them on top of our clusters? Well, let's say if we are in an OpenShift cluster, any cloud, you go to OpenShift Operator Hub in the administration panel of your OpenShift cluster, and then you have the Operator Hub with the operators which are already displayed there, and you can deploy them on top of your cluster, and you can use them, play with them if they are trial for a moment, etc. So the first place to look at is the OpenShift Operator Hub if you have already an OpenShift cluster. The second place where you can find operators is the site operatorhub.io. So operatorhub.io is kind of GitHub for the operators. You've got operators which are ready to be deployed. You can test them and see and figure out how they work. You have the same as you can find on GitHub. You've got some which are trial, some which are free, but in any case, you can deploy them on top of your clusters, any cluster, not only OpenShift, but also, and look and figure out how they work. The third site where you can find operators is the Certified OpenShift Operators website, where you can find operators which are certified by Red Hat. Okay, so when we talk about certified operators, it means that they have been tested for very long periods of time, some months, and they have been approved, and they are kind of rock solid and bulletproof operators. So if you're looking for enterprise grade operators, the Certified OpenShift Operators site is the site that you should go and find the operators you need. Finally, the last place we can advise to look for software and operators if you want to deploy them on top of your cluster is the Red Hat Marketplace, where you can find a large variety of operators and third-party operators provided by IBM, provided by Red Hat, and you can try to install them and figure out how they work, or if you have a precise idea of what you want to install and set up on top of your cluster, you can go there and fetch the set of operators that you're looking for.
So thank you for listening to our masterclass today from our team of experts from the Build Labs. I'd just like to say a few words about who we are and how we can help you and how to get involved with us. So as we've demonstrated, we really do work hard to build those reusable assets and really understand how automating the operations of solutions can really help meet the demands of clients and open up new routes to market. We really do move fast, and we actually do the work with you one-to-one with technical support and guidance for our top build partners to help them build that validated technology. And then we also share our knowledge with original assets to enable our partners with modern hybrid cloud development skills. So if you'd like to get involved with the team and work with them, then really we're looking for applications that are already built for Red Hat OpenShift. Or if they're not, then please do speak to us and how you engage our wider Build Labs colleagues to help you with that work to move to OpenShift. You'll also need to be prepared to assign some people to co-create with our team during the engagement, which would take approximately 6 to 12 weeks, depending on the complexity of the application. So please do speak to your IBM seller and engage them. Talk about how you can involve IBM Build Labs with your operators to help you reach more clients. Thank you very much for listening to us, and we hope to hear from you soon.